Okay, so welcome you all to today's Halmstad Colloquium talk by Mike Brics. So Halmstad Colloquium series is a distinguished speaker series which has been arranged by the Center for Embedded Systems, Research on Embedded Systems, and Center for Applied Intelligent System Research. And it's a distinguished series which is held in sponsorship with the Knowledge Foundation. So we have the pleasure to have with us Mike Brics. He's a senior technologist at Synopsys, and previously he has been architect at NVIDIA, and he was also the chief architect of Ambric architecture, which probably will be presented some thing in the talk. And Mike has almost 50 patents to his credit, mostly in the computer architecture, design, and probably programming model stuff, and things like that. And one of his paper on KPN got best paper in 20 years in the prestigious FCCM conference. And also one of the things that Mike is known for is that he is leading an activity of organizing this top 10 predictions for the next 5 years, actually. Yes. And I was there in 2011, and there was one of the top prediction was that Mike will still be presenting it in 2016. So with that, I give the floor to Mike.
Okay. Thanks so much, Shane. And thanks very much. I'm deeply honored and very grateful to be able to come here and be with you today. And also, especially grateful, and I've really got great admiration for the work that's been done here in the Center for Research on Embedded Systems in the Kahn process network model of computation, especially based on the Ambric chip, which is part of what I'll talk about today. Ambric was a startup company in Oregon in the USA from '03 and then ran smack into the crash that we suffered in 2008 and ceased to exist. And the group here at Halmstad with Professor Svensson and Professor Zainul have really kept the lights burning on what we found to be a very effective and very productive way to do high-performance computing for embedded systems. So I have continued to work on it in my own time between NVIDIA, between Ambric and Synopsys. I worked for NVIDIA, as Zane said. But I've continued working on this on my own time, and hope to have a KPN implementation on FPGAs ready to release as an open source project in a few months. So I'm very grateful to be with the rest of the community here, of people that love and understand this architecture. These are the main points. Kahn process network is a well-known model of computation that's been around for many years, but at least in my view, it's been underused. It's especially well suited for embedded computing, any kind of streaming data, media, image processing, any kind of real-time, very compute-intensive streaming. It is remarkably easy to learn for a general programmer, remarkably productive, and it has modularity and reliability and scalability, which are really valuable properties for going forward in embedded systems like this. Ambric, as I said, was a silicon startup, and we implemented a KPN in silicon that I'll show you. And that was commercially released in 2007. And the main reason I talk about that, obviously I'm proud of it, but it was probably the largest example of a KPN that was brought to the general engineering community as a potential solution for high-performance embedded systems instead of using an FPGA or a DSP. And it found very good acceptance and was applied in a number of different applications. The technology generally was very successful. And it's unfortunate that, for business and economic reasons, Ambric was this close to, achieving orbit, as I like to say, and surviving. But it did show the value of the technology, and that's why I continue to be excited about it. Today's FPGAs are really, really ideal platforms for implementing KPNs, and I'll talk about that. So first, the talk is Kahn process networks in silicon. So let's look at this model of computation and look at how we can implement it in silicon. To be clear, we're actually, I think, very fortunate to be working in embedded systems as computer architects. We are not addressing general purpose applications. An embedded system typically is focused on one job, and it has to do that job with much higher performance and power efficiency than a general purpose CPU. Otherwise, you would just use an ordinary CPU there. And it's usually power constraints, which of course nowadays in all forms of computing there are power constraints, but embedded systems have been dealing with power constraints forever. Size and cost constraints as well. Real-time constraints frequently involved, as we know in embedded systems. Safety is often an issue, so determinism is an especially valuable property. And reliability, sometimes remote service. Even if it's a cell tower up on a hill or a probe on another planet, sometimes embedded systems need to be serviced remotely. Here's the big thing that liberates us as computer architects and engineers working on embedded systems. The hardware and software is typically redeveloped to a great extent, sometimes even completely replaced at each new silicon generation. At least the highest performance embedded systems developers have that expectation. It is unlike what is always the case in general purpose computing, and even to a very great extent in high performance scientific computing, where there's a standard operating system and standard applications, and whatever you do in the architecture of the hardware and the tools, you can't touch the old code, or you can permit very, very small changes. That's incredibly confining. And, people get very excited about getting a 2% improvement in the hit rate of a cache. And that's very important work and very valuable in that field because of the leverage it has. But I think as architects and engineers, it's very confining to innovation. We're lucky in embedded systems that the application target, that the users, the developers of embedded systems are open to new ideas. If you can get better performance, better power, and it involves redevelopment, they are open to hearing about that. So it's a great opportunity for new models of computation. So, we like to ask, what's a good parallel programming model? Okay, what is familiar and productive and scalable? And it really comes in two forms. Naturally, software engineers are much more common than hardware engineers or specialist DSP engineers. And if you can express the computation in a conventional sequential form using a conventional language or a subset of conventional language, that's very desirable. So a serial processor is a very, very good building block to have. So for parallelism, we'd like to have an array of serial processors. Well, how do we get these serial processors to work with one another? Well, they're really the fundamental properties of parallel computing. You've got the processing, but then how do the processes communicate, and how do the processes synchronize? These are fundamental concerns in parallel computing. Block diagrams are familiar. And even people that are not thinking in computer science terms at all, and they're thinking about, I'm doing a video encoder, or I'm doing some kind of radio signal processing, how will they start? They'll start with a block diagram. I've got this function, it flows into that function, and this function, and so forth. There's a natural, implicit kind of concept of specialized functions that are passing data and control to one another. So a block diagram is a nice way to do it. And then finally, if we can take advantage of that and maintain encapsulation and use hierarchy with standard interfaces, then we can get lots of reuse, because the most severe constraint is development cost. And of course, we want to get as much reuse as possible. There are many models of computation. The Kahn process network is the one that really is what the Ambric architecture landed on, and is the one that we really stuck to and found to be very successful. Kahn wrote about this in 1974. He worked with McQueen. It's often called the Kahn process network or the Kahn-McQueen process network. And it's very simple to explain. You have a number of processors, processes, and they're sequential processes, and they all run concurrently. Okay, that's easy to understand. And they communicate to one another strictly through FIFOs. Okay, there is no shared state. The state of a process is confined to the process. And these processes only communicate and exchange information, exchange data, control, through these communication channels, which are FIFOs, first in, first out. Now, in the pure form, the theoretical form of a Kahn process network, those are unbounded FIFOs. And what that means is okay, a processor is a consumer. Okay, it's expecting to receive a word of any kind, a token, a data, whatever it is above the level of the model of computation here. It expects to get a word from a producer that it knows is connected through a channel. And the code is written that way. It says, okay, get this word. If there's no data available on that channel, the process blocks. In other words, if the processor is just dedicated just to that one process, the processor stalls. And it waits until data becomes available. When data is available, it consumes it from the FIFO. And it cannot poll. And I don't have time to go into why that's important. But if you observe the strict constraint that says the process has to block, it can't say, well, if there's data, do this, if not, do that. By having this constraint that the process has to block until data is available, all kinds of nice theoretical properties. I mean, basically, it's fundamentally deterministic. The consequence of that is that you have deterministic execution. Okay. And then, if we're going to implement it in silicon, we can't have unbounded FIFOs. I mean, the model says that the FIFO is never full. And there are ways in software that you can make it pretend that the FIFO is never full, but a common constraint, a common form of a KPN, is to have a KPN with bounded buffers. In other words, a FIFO can become full. And then likewise, if a process that is a producer is trying to send data into a channel that is full, either because its consumer has stopped or for whatever reason it's full, well then it blocks and waits for that channel to free up. Okay. So it's a very simple concept. From the point of view of any given process, it's just a serial process running code. If it has data, if it wants to consume data, it tries to consume data from a channel. It can have many channels that it consumes data from other processes. If there's no data there, if that channel is empty, it waits, it stalls. If it has data to push out on a channel to some other process, if the channel is full, it stalls. If not, it produces data. As a mental model, a very simple mental model that I like to think of, it's kind of like in the old days when computers were people. And you may have seen pictures of these huge rooms full of rows and columns of desks and people there with adding machines. And there's an in basket and there's an out basket. And the person has a certain amount of work to do. Or production, manufacturing used to work this way too. They just do their stage of the computation. They don't know anything about what anyone else does. In fact, in the Manhattan Project, they did things this way because that's a good way to keep secrets. That's the point. Any given process only knows its own task. It only knows what it does. And it has an in-basket, or maybe many in-baskets from different other desks. And when the in-basket has work, it can take the work and it can compute, and it can put work in the out-basket. Okay? If the in-basket is empty, well, naturally, you're just going to wait for something to show up. Okay? You're going to have a cigarette or whatever and wait until something shows up. And likewise, these out-baskets, let's say, you know, they have a limited capacity. If they get too full, it'll fall over and we'll stay out of order. And so then, you know, if it's full, it'll wait until somebody takes the work. It's that simple. Also, I kind of touched on this accidentally just now. Everything stays in order. I mean, these channels being first in, first out, they maintain order. And that is synchronization. So we'll talk about that. They strictly preserve sequence. So we call these things objects. And an object simply exchanges data and control through a structure of channels. And these are asynchronous at the system level. Okay, you notice I haven't spoken about time. And that's what allows it to be deterministic. The only events in the system are, you know, data arriving on channels. And so that's asynchronous, which is a very nice property. In silicon, an object can be a processor, obviously. It can be a hardware block, too. Obviously, in interfacing to the outside world, an object could be an interface to a peripheral. Let's say it's a video input, and that's a process that only has output. It receives output at a certain rate, and it feeds it out at that rate, which indirectly turns out to determine the whole rate of the computation. Likewise, for an output peripheral, a memory block could be a process, or a set of objects. So it has this nice hierarchy. Because the only interfaces are channels, you can compose and have a composite object, and you see the only interfaces are channels. So you have this natural hierarchy. You can have an FFT object that you don't even know if it's processors as a programmer. You know, maybe it's processors, maybe it's a hardware block. You just say FFT object, and you drop it in, and it has channels just like any other object. So you get nice hierarchy that way. Thus, at the top level, the application, the whole application is itself a single object. It's a composite object. Okay. That makes it easy to think about, easy to develop, and very scalable. This is the way I like to explain it to regular programmers, people that are not into models of computation. But, you know, like I said a minute ago, we all draw block diagrams. So, you know, let's have each block be an object, or whether it's a simple object or a composite object. And then, you know, inside a simple object, you can write code. And, you know, maybe this code is going to send an output out on a channel. Well, that's just a function call, okay? So it's pretty easy to understand. So like I said, to be a little more specific, a processor object can simply be a processor running code. It has its own state. It has its own local memory, its own registers, okay? So there's no looking into another processor's memory, which is a convenience, but it is a convenience that is so fraught with peril, as we know, in conventional shared memory parallel computing, that by saying, no, you cannot do that, you're free from, you know, mangling each other's pointers. You get excellent encapsulation that way. Once an object, it only has its own state, it only has its own memory. Once it's debugged, it stays debugged. And something else can't go in there and damage it. And we found this in practice. I mean, once you get an object debugged, you can just use it. And you can compose systems this way, and it's very reliable. Alternately, an object can be implemented in hardware, as I said, and then, of course, any kind of objects can be connected to one another to make compound objects. And you can carry that hierarchy as far up as you like. So those are the kind of objects that we're talking about in silicon when we take a KPN and we map it into silicon. A channel in silicon is a FIFO, and any given silicon implementation, we choose a particular hardware interface as a way to, I guess I can use this as a pointer. Yeah, I guess. I don't know if it's meant to be a pointer, but it works. So we have a data path, and we have FIFOs. And in addition to the data path, we have some simple flow control. And this really corresponds to empty and full. If a FIFO has data that's valid on its output, then it has a valid output, which is true. Okay. If a FIFO has space to be able to consume data, then it issues a backwards flow control signal, it asserts, that's called ready. In other words, if the FIFO is not empty, valid is true. If a consuming FIFO is not full, then it's ready. Okay. So let's assume these are in the same clock domain. And so on any given clock cycle, both sides can see, okay, the valid is true and ready is true. Valid is true, ready is true. Both sides, they can see, okay, then that means this cycle is a transfer cycle. And so this timing diagram just illustrates that. Okay, if the first FIFO has data, but the consumer is full, then it will stall and no data is transferred. The data appears, but it's not transferred. Then we get room in the consumer, and now we can do the transfer. One key constraint here, just like, you know, FIFOs are. I mean, if a FIFO says it's not empty, and you haven't consumed anything, it's not allowed to, in the next cycle, say, well, now I am empty. You see what I'm saying? Once this valid signal has been asserted, you can't unassert it. That's against the rules. And it's against the nature of FIFOs. Likely, if a FIFO is not full, and the only thing feeding into the FIFO hasn't done anything, well, then it can't suddenly say, I'm full now. Okay. Now, that's obvious and maybe silly in the context of FIFOs, but see, the object interfaces have to work this way too. The processors have to work this way. That's why you're not allowed to poll. So you get the general idea. And the effect of that is that they have full forward and backward flow control. Okay. Now, in terms of bandwidth, this can clearly, data can move forward here at 1 word per cycle through any number of these things. Let's suppose, for whatever reason, the consumer here stops consuming. Okay, well, this FIFO has 1 word. If we've been sending a word per cycle, it's got at least 1 word in it. Okay, but now it cannot, let's say this ready line is low, and now it cannot, it has to keep that word. It can't give it up. So it has to always have at least enough room to receive a word because it's been saying I'm not empty. All right, that's necessary to maintain the bandwidth of 1 per cycle. So what that boils down to is that at any given stage, the minimum size of a FIFO is 2. And if you have a FIFO with capacity 2, in this context and at Ambric, we call that a register. And what that means is that if a stall occurs, then it can, catch the word that's coming and propagate that stall to the previous stage. And the very important consequence of that is that there are no wires longer than 1 stage. Okay? There are no wires anywhere in a KPN in silicon that are longer than 1 stage. This is very scalable. No long wires. Okay? And when a stall occurs, that propagates backwards at 1 stage per cycle. And then, of course, when it starts consuming again, then it unwinds that and goes forward at 1 stage per cycle. We call that a register. Call it what you will. That's the key. So that's a channel in silicon. So let's have objects in channels in silicon, okay? Well, the object itself, its interface, has to behave exactly as if it's a FIFO. Okay. And when you think about it, if this is executing code, let's say it's not, it's busy in some loop and it's not ready to accept a word. Well, then it's going to say not ready. It's as if it's a FIFO that's full. Okay. Then it gets to an instruction where it says, okay, I can accept this word now. Then it's going to assert ready. Now, if the word is there, then it'll see that the valid word is there and the word will transfer. Okay. If the channel's empty, it'll stall. All right. It'll just stop there and continue asserting ready until a word comes along. And then likewise on the output. So the objects themselves, the processors, hardware blocks, whatever, their interfaces have to behave like FIFOs. When you do that, it's fully encapsulated. And everything is asynchronous. This process doesn't know or care anything about what else is connected to it. So it's got this really nice encapsulation. The really big thing is, I said before, communication and synchronization. I mean, that's a real pitfall of shared memory parallel computing, is often the communication and practically always the synchronization is put on the programmer. The application programmer has to deal with synchronization, to make sure that all of the processes stay in step. Okay. This is intrinsic in a KPN. The act of transferring a word from one process to another is obviously communication. It is also synchronization. They're the same thing. You cannot communicate without synchronizing. You can't synchronize without communicating. And that's a really nice property to have. Also, since there are no long wires, it's very easy to do globally asynchronous, locally synchronous clocking. Okay. FIFOs are natural clock boundaries. And I show this here all in one clock domain, but it really wouldn't matter if there was, 2 clocks here and we had a clock domain here, if there was a clock crossing through that FIFO. So that makes it physically very scalable. I got ahead of myself. I actually have a slide about this. See, the processor stalls if it's got output to do and the output is not ready. In other words, this cannot consume for whatever reason, it's full, then it stalls. So it'll just execute and it'll just stall there. And then likewise on input, if this channel is empty and it's to the point where, okay, I want to get a word, it'll stall. Okay. Now you might think that that's inefficient, and it can be. But in practice, when you get your system developed and you think about bandwidths as you lay it out, and then you run it and you see maybe, I've got a processor that's idle too long. Well, there's 2 responses you can have to that. One is, so what? Processors are cheap. Processors are very, very cheap. So what if it's idle? Okay. If it fits on the chip and everything works, we're happy. Doesn't make any difference. And it's stalled, so it's not consuming power. Or you can say, well, let's give that process more work to do. And so, there are 2 different ways to respond to that. But the developer doesn't have to deal with hardware issues like synchronization or timing closure. Okay. It's self-synchronizing. Finally, and mainly I've got this here so that you can understand the little example I'm going to go through. It's nice for the interconnect to have specialty objects that allow the topology of the interconnect to, have forks and joins. The idea here's an example of where you want to have 2 channels and you want to merge the 2 channels together. Now, that's a process, and that could be arbitrarily complex, depending on what you're actually doing. Frequently, it's nice you frequently find that you want to have a very simple process that just takes a word from here and then takes a word from there and interleaves the words in a deterministic way. Okay. You can spend a processor for that, but if you can build that into the interconnect, it's simple and it's more effective. For example, and then likewise, to fork, you have a word come in and maybe you want to distribute. Maybe you have the kind of work where one process, the processor's not fast enough, and the nature of it is that you can pass a word to one processor and then pass the next word to another processor and divide the work that way. Okay, well, if you do it alternately, an alternating fork can do that for you. Okay, and if it'll stall indefinitely if it's A's turn until A consumes, and then it'll offer one to B, and back and forth like that. Okay, so for example, you can distribute work with an alternating fork to 2 copies of a process, and then collect results with an alternating join. And it's an easy way to do it, and it's nice to put that into the interconnect. And there's other variations that are useful. And so we'll get to an example here in a minute. But let me first briefly touch on, I don't have time to go too much detail in here, but, and this is a bit of an arm wave. Maybe this is a good problem to give a student to, build the real foundation underneath this, which, we've thought through. But basically what you're doing here is by making the interactions between the objects simple. Let's put it this way. In a shared memory computer, you have n processes running. Any 2 of them could have a relationship potentially, constructive or destructive. Okay? If you double the number of processors, you quadruple the number of possibilities. Okay? So a real problem with massively parallel shared memory computing is that the potential number of relationships just explodes. With this system, any given process is only interacting with the processes it's connected to. Okay, so that's constrained. So in a sense, you're taking a super linear situation and scaling it back down to something that's linear. And that helps debug, it helps scaling for performance, and it certainly helps effort. This is a very arm wave kind of slide, but we could do a whole talk just about that. Be an interesting thing to do. Okay, let's look at a simple, and this is a very crude, but I found effective way to have an example. We're going to issue an ordered list of prime numbers. Okay, and we're going to use the simplest, stupidest, most inefficient way to find prime numbers, simply because it's a nice way to illustrate how a KPN can work with communication and synchronization both. Okay, basically, for each odd number, divide it by each smaller odd number, and you find that if it divides without a remainder, it's not prime. This is really dumb. But it shows how objects can work together. And it's a challenge. I mean, if you just say, okay, let's just take this as an algorithm, and how can we have parallel efficient execution of this algorithm, it's interesting because the execution time of any given step is very irregular and unpredictable. Okay? It might take 3 steps, it might take 22 steps, it might take n over 2 steps. To keep the list ordered, you have to synchronize. And to keep all the processors busy, you have to buffer. Okay, so here we are. We have 4 processes, PG1, 2, 3, and 4. And we arbitrarily divide up the primes among them, the odd numbers among them. Okay, and each one, it takes its number and it tries to see if it's prime. Okay, if it is prime, it outputs it. Otherwise, it has concluded that it's not prime, it issues a 0. And that's simply a token so that we can preserve order. Okay. We have FIFO buffering. We have an AND join. This is an ordered join. It waits until both inputs are available. And then it will it'll accept the two inputs in a specific order, as you'll see, and issue them in order on the output channel. Okay. And this is finally a cleanup object that deletes the zeros, and now the result is a series of prime numbers on the output. Okay. So the first thing that little utility object does is it issues a 2, because 2 is even, and it's the only prime that's even. So this thing's trying 3, and it found out right away that 3 is prime. This is trying 5, and that's trying 7, and that's trying 9. Okay. Well, so each one, you can see we have 3 divided by 3, and it does divide, so that's prime. Okay. 5 divided by 3 has a remainder. 7 divided by 3 has a remainder. 9 divided by 3 is 0. Okay. So we issue a word here on this channel that says, yes, it is prime. There's 3. A word here that says, no, it's not prime. That's a 0. Okay. Now it's trying 11. Now this, after it tried 3, it tried 5, and it got to 5, and so it knows that 5 is prime, so it issues it. Okay. This is still busy trying to divide by 7, and here we're doing the first step of dividing by 3. Okay, and in the meantime, these have propagated. This 3 now has made it to this join. Okay, but now it's not going to propagate anything until something else shows up here. Okay, now the 5 makes it through here, and so it can now pass those through. And it does them in order, and so first it issues 3, then it issues 5, and now here's 7. And so it passes 3 and 5 through, and then it adds the 7 to it. Basically, this join is designed so that it'll, as long as it has input that's ready, it'll pass it through, and then when it has emptied that channel, then it'll go to the other channel. Okay, that's how it can do that merge. You know, you see, since 9 is not prime, the 0 passes through. Now these are still chunking away, trying to find out. There's 11. It found out that 11 is prime. It found out that 13 is prime. It found out 17 is prime. And so it's just moving along like this. And you see, then the 0 is stripped out. So I hope you get a sense of how the rules of the KPN can be used with these join processes in this case, and the buffering that's necessary to allow you to have an ordered computation where everything is only locally synchronized because of the way you've arranged it. Okay. Let's see. Oh yeah, this is interesting. Here, let me go back. Okay, now see, this channel has a 0 here. All right. If we didn't have that FIFO there, then it would, you know, this channel would be full and it would have to stall here. It'd be stuck. All right, and that would waste performance. By putting a FIFO there, we can get better performance. And that's a fundamental principle. Okay. So a little buffering allows processors to stay busy. That's the takeaway. All right, so each object is simple. Synchronization is intrinsic, and if you use FIFOs to smooth out the irregular runtimes of the processors, you can do good load balancing. Okay. So I'm going to talk briefly. I've got, if it isn't already obvious, far too many slides. I did that on purpose because this will be available online, and I just want to kind of highlight things, and I'll be here all week. And you know, if you want to learn more, let's talk about it, or later you can you know, see it on the slide. I'll be happy to talk to you by email after this week. The Ambric 2045 was released in 2007. It's a medium-sized 130 nanometer standard cell ASIC, which was a very conservative process at the time, pretty inexpensive. And it's made up out of Brics, 7 by 5 array, and 42 of them are these Brics. And a brick is simply a richly connected cluster of processors, 8 processors actually, and there's 2 different kinds, and 8 small memory blocks, okay? And then in addition, each processor has its own small instruction memory. Total of 4.6 megabits of SRAM for code and data and for FIFOs, okay? And then there's exceptions here, special purpose blocks. You might think of these as hardware objects. In fact, I think you should think of them as hardware objects, these 2. You know, that's a DRAM controller. And you say, well, wait a minute, you know, we have a large DRAM, how does that fit into a KPN? You know, maybe we're doing video and we have to have a frame buffer, okay? Well, an object is certainly allowed to contain memory locally, okay? And if we want to have shared access to that memory, we connect channels to it. And each channel says, you know, I'd like to read or write this location in memory. Each channel can do that. It's managed. You need to do, well, there's ways that, I mean, this is the case if you're explicitly sharing memory. Now, it's up to the programmer explicitly to manage shared access, okay, and there are many ways you can do that. It's an object, all right? So memory itself can be an object, and so this DRAM is an object. It is only readable and writable by the processes that the programmer has connected it to, okay? Not by anything else, and only through those channels. So there's 2 of those. This is a neat little VLIW microcoded engine that we did because we ended up in the H.264 video encoding. There's a binary coder at the end called KBAC, which is a real tough little nut that has a lot of operator level parallelism, and it's a finite state machine. And you can't split it up to have copies of it to get more performance. So we did a little VLIW to do that, and it just has channels. So we were able to just throw that in there instead of the regular processors and memories. The channels connected to the system, the other processors don't know the difference. We actually added that late in the process when the people implementing the video encoder went, oh my gosh, we can't do KBAC. So that was nice. And then it has an FPGA-like interconnect structure. I actually used FPGA tool algorithms to do the placement and routing for the automatic placement and routing tool. The idea here is that processors, that you can program this network of channels as you do an FPGA, you know, so that the actual channels connecting processors can be routed with dedicated channels, dedicated buffering. You can route them through FIFOs. That's static. And, you know, the topology of the KPN in silicon and the composition of its processes in KPN in silicon is static, okay? Now, KPN is interesting in that it can be dynamic. There's a lot of good work on having dynamic KPNs where processes come and go. And that, you know, we may grow to address that, but for now, for starters, in silicon, the KPN is static, okay? And we have this hierarchical interconnect. So you have direct channels available to connect, like if a processor here has a channel to a processor here, then the router will assign a hardware channel with a direct nearest neighbor connection. Or for longer connections, we have, you know, a multi-hop. You can route, you know, through here. That's a statically programmed switch to route that channel here, to route it over here, to route it there. Again, it's kind of FPGA-like. But it's far more reasonable than an FPGA because we're talking about hundreds of processors and channels, not millions. So the algorithms are similar, but they run very fast. It had a processor cluster of 4 processors. 2 of them are DSPs, 2 of them are just simple integer processors. Lots of fun detail there that we can talk about offline if you're interested. This is the simple integer processor, and here's the key point that I really wanted to show you. The thing that's kind of interesting about, all right, how would I do a processor for a KPN? Well, if you're an instruction set RISC kind of a geek like I am, you say, well, fine, we have an operation, and we have source, and destination. Well, they don't have to all be registers. And that's what we ended up doing, is we said this source1 field can be a register, or it can be a channel. And so these fields can be registers or channels. And then on the output side, this is one of the channels, or no channel if you don't have output. This is one of the registers. Okay, so it's just like a, if I wanted to add 2 registers together and put them back in a register, just like in an ordinary RISC machine, I could certainly do that. If I wanted to simply have an object, let's say, that accepts a word from a channel, adds 5 to it, and issues it out on another channel, well, that would be a 1-cycle loop of an instruction where one source is a channel. Another source is a register that has 5 in it, and the output is to the output channel. Okay? And so you can be very efficient. You can, some KPN implementations get kind of heavier implementations where, accepting something from a channel takes a number of cycles. We want to do high throughput signal processing here. So we need to be able to handle, one operation per cycle and be able to feed that. So intrinsically, the instruction set architecture has this capability where the channel is on the same level in the instruction set architecture as a general register. And that's why we didn't use an off-the-shelf somebody's ARM core or something like that. This is actually very simple, very bare bones, and very small. Very few transistors. This is similar. It also has a multiply accumulator that's double width, 64 bits, and so this is essentially a DSP. They each have their own local memories for instructions. Now, that has the unfortunate side effect that it can get full. And at least in this first simple, KPN in silicon, there's a limited length of the program that you can have in a process. Okay, it turned out to be pretty good. We got the sizes pretty much right. But again, this is a very, very different experience to the programmer than, well, I can have a code as long as I want, and it'll have cache misses, and it'll have page faults, and who knows what the performance and who knows what the dynamic behavior will be. This is kind of taking the radical other step and saying, look, it's here, the code is here, it always takes a cycle, it's very predictable. Okay, that's not the only way to do a KPN in silicon, and it's very interesting to think about, this problem. But that's what we chose, and I think it's a good place to start. Then it also has a collection of RAM blocks, little streaming engines that can implement FIFOs, and read-write access. And by the way, the processor doesn't have a load or store instruction. Well, except to its own local memory. Okay. And it has an instruction that allows it to do a single cycle loop. That's important. All DSPs have that, and this has that too. So you can set this up to do a multiply accumulate, and it'll do a 1 multiply accumulate every cycle. And so if you want to do a FIR filter, you can have a FIFO that works as a circular buffer with the coefficients and feed that into one channel. Okay, and then you can accept a sample in the other channel, do the multiply accumulates, kick the sample out, and then, it's a circular FIFO, so the coefficients just, come around again. Okay. I don't know how meaningful these are 5 years after the fact, but we were very happy with these performance numbers. We called it a tera-op chip because when you count everything, including we had a sum of absolute differences operator, which is critical for digital video. Trillion operations per second in a programmable, software programmable, modest-sized chip. And, very rich interconnect bandwidth, very high memory bandwidth. This will give you a flavor of the things that were important in the target applications, maybe is more to the point in today's talk. The target applications that care about things like this. Signal baseband, signal processing, encryption, filtering, video. Your high-performance signal processing. So how do you program this thing? If you're familiar with the Eclipse IDE, it's all built inside Eclipse. I can't believe it's 5 minutes after 2. I could talk about this all day. Pretty much the way you would expect. You would write the objects, and then you would express. At first, we only had a net list. But basically, each process has code, and then there's a net list that says how they're connected. And they're, the ports are named, and so, that's how you connect it up. And then the compiler would automatically compile the code into assembly code for the objects, place them in the physical array, and route the channels that you've specified, and so that it knows how to program the chip. And so then, having done that, this is sort of like an FPGA. Then at runtime, you load that into the chip, and the KPN now is all programmed and runs. This illustrates, the kind of programming. Here's how you program an object. This is a selection of, for this processor, it's got these objects, and it's hierarchical. We use the subset of Java because Java hasn't got pointers and lots of other good reasons. To write out to a channel is simply a function, and it's a named channel. Debugging was really nice. At runtime, it's very easy to have, we had a simple hardware monitor underneath everything, so we could look at the activity of all the processors. So at runtime, you can see how busy a processor is. And then also, you can just single step. And that's something, again, where the KPN really helps. Something that's great about a KPN that's very important is its determinism and the fact that it's not tied up with time. And the fact that the synchronization is in the communication means that if you have a system and it's running at full speed, and you open up the debugger, and you say you stop a process, you say stop, okay, well, it's not going to just crash. What's it going to do? It's going to stop consuming and producing, all right? So upstream, those buffers are going to fill, and those producing processes are going to stop. They're all going to stall. So everything stops upstream in a natural way. Likewise, downstream, everybody starves, and they stall. And then you can look, and you can step, and you can, do it one step at a time. You can go in and change state if you need to. And then you can say start, and you don't have to reinitialize and rerun, because you haven't messed up anything. It'll just pick up and run where it left off. Which is really fun, really productive. We had a nice performance analysis tool, okay, to show us how busy the different objects are over a longer period of time. It's very easy to do tracing. You can just add another object for debug. You can put a fork in here that all it does is a duplicating fork, okay? And so that just taps the channel. And again, because it's not dependent on time, all right, it adds latency, but it doesn't change the sequence. So it still runs the same. So, and you can write whatever debugger tool you want. And then, like I said, we had this fabric underneath so that you could look at it. If it deadlocks, parallel programs can deadlock. And someday, if we have a model of computation that, has properties that we can address with formal analysis, maybe, we'll get better at being able to find deadlocks analytically. But for now, if you wrote it and it has a deadlock, it's just going to deadlock, or a live lock, and boom, it'll get stuck there, and you'll see it, and you can debug it. and you know, fix the bug. Okay. I'm going to blow through some application examples just to give you a flavor. This is the actual structural composition of an H.264 encoder that was implemented on the Ambric. Okay. You see it's got feedback. One thing that's really tricky about H.264, one reason it's so powerful, is that it has its own decoder inside it. So it knows what the state of the decoder is going to be at the receiving end, and it uses that, you know, to be smart about sending less information. There's a deblocking filter, which is particularly nasty because it's got a very irregular problem. That's another, as kind of interesting. I mean, these things, signal processing seems very simple and regular at first. But as it gets more and more sophisticated, it gets more and more complex. And H.264 is twice as good as MPEG-2 because you have a choice of lengths and coefficients and threshold. You have choice of filters and choice of encoding depending on the runtime situation. All right, so now there's a whole lot more complexity. This thing is not just flowing. And this is problematical. It makes for very complex hardware if you're going to do this sort of thing in Verilog. Very hard to debug. In particular, it means that the different levels of hierarchy in the data can take different paths through different functions that take different lengths of time, different numbers of steps. So it's very challenging for synchronization and load balancing. And so what we did at first is just implemented a simple filter, okay, and then this is the feedback that's part of the functionality of the deblocking filter. Okay, but let me point out something. Here, this is just a filter with a certain bandwidth. We realized, oh, we need more bandwidth here. Okay, so two objects are put in parallel here to get more performance with forks and joins. And then there's the filter strength selection part. And likewise, bandwidth increase with multiple objects here. These are how big the FIFOs are. A FIFO can be a certain length just to provide enough slack for the feedback, or it can be storage. I mean, if you're doing video that's line-wise, you know, if you have a FIFO that's a line long, then that's the vertical direction, right? And so that's how you do things vertically, is you can put it all through FIFOs. And that's way better bandwidth than reading and writing from a frame buffer, all right? So, you know, it had these characteristics. It never read or wrote the frame buffer, so that's way better for both performance and power. Okay, it kept the data moving. But we had a load balancing issue that I don't have time to go into. The target was 3.2 cycles per sample. In the final design, it was 10.2, and in theory, it should have been as low as 2.6. Okay, so what's the solution? Rate balancing FIFOs. Well, how do you figure that out? Well, we have profiling objects you can put in, okay, to observe the behavior. And the programmer simply tried different places to put FIFOs and different sizes. I mean, these are engineers, are smart people, and they're good at solving problems. And it's not too hard because it's easy to turn the design around very quickly. So eventually you find, you try this, you try that, and you know, it turns out that if you put FIFOs here and they're big enough, you can get the bandwidth down. This is not analytical, it's practical. But because it's an easy architecture and it's pretty safe and you can turn the design cycle around quickly, you can do this kind of thing, okay? Motion estimation, there was a WiMAX Phi signal processing. Medical ultrasound was an exciting application. This was the coolest. Triple Ring Technology built an X-ray system for Novaray, which is a tomographic X-ray, where there's a low intensity X-ray source and many X-ray sensors, then computational tomography. And they built a system where each card had 8 of these Ambric chips. You could connect the Ambric chips to each other. That's just a slower channel. It was very easy to have multi-chip applications. So the whole system had 4 of those boards and 4 more on another board, so there's actually 36. We had over 12,000 processors in a KPN that they developed the application for, and it ran. It worked, and they did it in under a year. 12,000 processors in a KPN in real silicon. I really want to point out how valuable it's been that the group here at Halmstad has done a lot of very interesting research on applications and also on program development. Occam-Pi, that's a parallel version of the Occam language where you can express the entire problem in one language. There's not processes and net lists. So that's very interesting. This has really been helpful. BYU, University of Washington, we had 15 members in our university program, and at least 10 of them were active, and a few had published by the time we closed. So that was Ambric. Yeah, here's the KPN. You can look at this offline. Very intensive signal processing for radar autofocus, motion estimation for compressing video. See, these are very different applications. What do we do now? Can't get an Ambric chip. It costs so much to make a chip that you just can't even start a company. I mean, Ambric would have barely squeaked through, but we had a heck of a time raising money because it just costs too much to tape out a chip. It's too risky. And that's the state of the silicon world that we're all in today. It costs an awful lot to tape out a chip. So if you're going to ask somebody to give you money for your new idea to tape out a chip, you're asking for a lot of money. And the numbers just don't pencil out. It is, even if your chip is brilliantly successful, it is unlikely that the investor will get the kind of return that they expect from these kind of investments. So it's not happening. Things have become very incremental, very conservative. So that's rough for people like us that really want to do something different in computer architecture. Fortunately, FPGAs are doing great. And they've gone from glue logic to being monster, very effective, very affordable ways to implement any kind of hardware. Okay? So what I like to think of is to take the approach where, well, oh yeah, I mean, not only that, there's actually a lot of what you need for a KPN is in hard silicon. Okay? In the current new series of Xilinx chips, not only is there a multiplier, it's a multiply accumulator with a full ALU. And that's the processor data path for a DSP, including the little bit fiddly logic operations, okay? That's in hard silicon. Likewise, if you want a FIFO, pick a block RAM, tell it FIFO, how wide, how deep, silicon. So, you know, what do you need for a KPN? You need processors, you need FIFOs. Well, they're in hard silicon in FPGAs, which means there's a ton of them, and they're very effective. So the idea here is to, you know, what is your FPGA design? Your FPGA design is a KPN parallel computer. Okay, you design that, you run that through the FPGA tools, then at runtime, the FPGA, you know, you load the configuration, and now it's a computer. It is now programmable at a higher level. We're calling that FPGA overlay. There's a new workshop that's starting at Berkeley, annual workshop in January, looking at FPGA overlays. The notion is that you're not changing the FPGA itself, you're programming it. It's just as if you're doing a tape out. But instead of 50 million euros and a year or 5, it's 100 euros and it's overnight. And, you know, boom, you've implemented your silicon. So that's a much more attractive. And then having done that, now anyone can say, okay, here is our KPN. How would I program it? And you're not reconfiguring, you're not using the FPGA tools, right? You're just programming your KPN. And I want my KPN. And so I'm writing one. It's mostly finished. I really, really hoped to have it ready to bring to share this month. But I had this little detail called a really great new job that was very sucked down all of my free time for the last 3 months, which is a wonderful thing. And by the way, I'm here on vacation for Synopsys. This is not Synopsys project. This is my own personal project and my own personal passion. Although, as I've already found, people here are interested in talking about things like formal equivalence checking and so forth. You know, if there's any kind of verification-related topic you'd like to talk about while I'm here this week, please stop by and I'll put on my Synopsys hat and maybe put you in touch with the right people. But no, this is personal activity. And it's a small KPN, very simple, 18-bit, basically just to get one out there with, you know, around 50 processors. That's a $200 development board with a Spartan 645 in it. Partly because so many people, especially exemplified by the work being done here at Series, need a research platform and a teaching platform to just get hands-on with KPN. So when I get it together, I'll share it first with Zane and eventually put it out for the research community, anyone that finds it useful. I hope we'll be able to use it. I want to do things on it too, and I'm hoping to have this available next year. Briefly, it's an array where it's much simpler. One CPU with the DSP and a block RAM for memory and data. Very simple CPU. Those are the details you can read about offline. And then the other component in a brick is simply a switch that allows you to wire channels together. And it has another block RAM so that you can have FIFOs, larger FIFOs between the processes. And the switch is also programmable so that it can do joins and forks. It's got a monitor bus like we had before. There's this wonderful open source facility called FPGA Link that runs on all platforms and all FPGAs that makes it very easy to get a very high performance interconnection between a PC host and an FPGA. Love to tell people about that. It's open source. It's a great tool. So you'll have a monitor. And of course, you can put hardware in because it's an FPGA. You can say, I want to have a version which has, you know, I want to have an FFT here, or, you know, whatever my hardware object is. So you can do that. In that case, of course, you have to get involved with a Verilog and run the FPGA tools and generate a new KPN which has this, you know, special hardware object in it. Potentially, I mean, this thing that I'm doing, I'm not even worrying about delay particularly. I'm just, you know, keeping it lean, and I'm getting 100 megahertz pretty easily. I'm sure that with effort you could get it up to 200. And in the inexpensive Spartan 6 chips, between 50 and 130 processors, the current generation on 28 nanometers with Xilinx is the 7 series. That's faster. And we can get hundreds or even thousands of processors with off-the-shelf silicon today. Now that is a $10,000 part, but you know, that is a $20 part. So, you know, the full range is there. And of course, FPGAs just keep going. So that's exciting. That's a wonderful platform. So, a little over time, KPNs are nice, and we had the opportunity with Ambric to bring them into real form and bring them to people and show that they work. And they do work, and people like them. And it's a good way to do embedded computing. And with FPGAs, we can keep doing it. So thanks very much for your time and attention. And I'm 10 minutes over time. I apologize for that, but I'd love to have your questions.
Let's say 10 minutes for the question and answer session. So,
yes.
Suppose I have a sequential algorithm without a block diagram. Is it more difficult to parallelize it for a KPN architecture than for a shared memory architecture?
Well, that's a good question. It probably is more difficult. Oh, I'm sorry. Yes, I need to repeat the question. Suppose I have a sequential algorithm, and I would like to speed it up through parallelism. Is it harder to do with a KPN or with a conventional shared memory? I'm sure it would be easier to do the programming with shared memory. It would be up to you to manage, you know, I mean, really to choose your model of parallel computation. It would be up to you to do the communication. It would be up to you as a programmer to do the synchronization. And then if you wanted to use it in a larger system and you wanted it to scale and so forth. So sure, and I think, frankly, that's why conventional shared memory multi-core programming is so pervasive. Well, for one thing, if you're running an operating system and you have many independent tasks that have nothing in common with each other, that's not really parallel computing, it's task level. At the processor instruction level, well, and then of course they've got this unbelievably exotic silicon that does instruction level parallelism, but that's limited. Processor level parallelism that's done automatically is limited. And as we know, that root is fraught with peril of, bugs with shared pointers and deadlocks and all those other things. So, but it's easy. It's easy to think of. We're all grew up with these computers, myself included. So in the short term, sure, conventional multi-core is easier. And for many applications, that's the reasonable approach. Most embedded systems today, I'm sure, have got simple ARM processors running a real-time operating system, and people write C code, and it does the job, and that's great, and people should continue to do that if it works for them and if it's fully reliable and it meets all the needs. But we're very challenged by the demand to get higher performance, much better energy, power performance. Determinism is a huge issue, and I think the KPN has properties that have been well researched over the decades that show that there is a potential for getting stronger solutions that are more provable with KPN parallelism in embedded systems. But I mean, you're never going to run Windows on a KPN, and no one would ever want to. Yes?
I was wondering, so you described both the use of FIFOs, both
yes.
for channels, but then you said that the interface of an object was also FIFO.
Yes.
The
yes. I've shown how we use FIFOs for communication and synchronization between objects, but I've also shown that the object itself behaves as a FIFO. And what I mean by that is, and maybe that's a little confusing to put it that way, because the object itself may or may not be buffering anything. I mean, its purpose is to process and to change, So, but the point is that its interfaces need to be FIFO-like, and specifically what that means is that it needs to adhere to the properties that this will behave correctly when connected directly to a FIFO, meaning that if it presents, all it's doing on an input is accepting word by word of data. It needs to behave FIFO-like on that, which is to say that when it is now ready to accept an input, that it will stay there and continue to be ready to accept that input. It's not allowed to say, oh, never mind, I'm not going to accept it after all, because that'll break down. So it's a FIFO-like interface. Another way of saying that is that to this FIFO, it thinks it's connected to another FIFO, and it behaves in every way as if it is. And then, of course, in the processor, we have many channels, and we do processing. And so that's an interface constraint. But it says nothing. This can be anything. This can be hardware. It can be anything. Yes, Berto.
Ambric is a homogeneous architecture, right? Although you showed that for some applications it might be good to introduce some heterogeneity as well. You added a special function unit.
Yes.
It's very much talked about heterogeneous architectures these days. Is there a good relation between heterogeneous architectures and KPN?
Very interesting and very broad question. What the KPN I presented and the KPN Ambric build was essentially homogeneous with a few little special objects that make it slightly heterogeneous, but there's a lot of work going on in heterogeneous systems. How would these two relate? something I blew by, but would direct your attention to is work done at Toronto by Paul Chow and Leslie Shannon, and Leslie Shannon now is at Simon Fraser in Vancouver. They did a project called Simple, SIMPPL, which was explicitly intended to be heterogeneous. And in that case, implemented on FPGAs and hardware objects, although it certainly wasn't constrained to that. I think they did processors as well. The point they were making in that work is that actually the way that Ambric came about is that a KPN with its interfaces and buffers and rules is an excellent way to interface functional blocks with one another of any kind, heterogeneous or homogeneous. So we might say heterogeneous function with a homogeneous model of system level computation. Another take might be, and I'm really looking forward to trying this, is all the special cases of having a KPN which is mostly heterogeneous, but has, for example, on the Zinc, Xilinx now has a chip they call Zinc, which is an FPGA with all the usual goodies, and an SoC. It's got a pair of ARM cores and the usual peripherals, and it can run Linux, it can run regular operating systems. It would be interesting to have a processor in a KPN that actually also happens to be running an OS. Maybe that's interesting. Maybe multiples of them are running, you know. Lots of answers. Lots of opportunities for research. Thank you.
Any other questions?
Yes.
Yes,
So when you described Ambric,
Yes.
then you mentioned the fact that so you set up the KPN for a given application,
Yes.
and then that's it.
Yes. Yes.
In the new version that you're working on with the FPGAs,
Yes.
are you planning to do differently there? So
Well,
you could, because you mentioned the fact that you could pass code also along the channel, so you could imagine passing code that rearranges the.
well, yeah, and to kind of summarize that question, the KPN as a model of computation, as originally expressed even in his first work by Kahn. Of course, at that time, we were only talking about one computer, and it was simply you know, a way of doing systems. And processes can come and go. It can be dynamic. The existence of a process and its channels can be dynamic, even recursive. In KPN on silicon, for starters, and maybe indefinitely, we've been assuming that the KPN's set of processors and connection of channels is static. And although there's some very interesting dynamic things you can do even on a KPN which has static processors and channels. And the second paper that I gave at FCCM was about that, work farms and things. You can send code through channels to processors and reprogram them to change their function. But it's static in the sense that there's a processor there and it has channels with a certain topology. With an FPGA, at first, we, I think, should maintain that static in silicon. And just look, you know, when you design for an FPGA, you write the Verilog, you express the wiring, and then you have a compile, and that takes a while, and then you have a file, and that programs the FPGA. I think of that as exactly analogous to taping out a chip. Okay, we all get $200 tape outs. And so I'm using it that way, and I suggest that that's a good way to start. If, let's say, I want to have a version of this KPN which is particularly good at, you know, something that needs a lot more FFTs, or something that I could express in hardware more effectively than I could in regular code on the processors, then I can say, okay, let's go back to the KPN's RTL representation. Let's take out a processor and put in some RTL function, recompile that through the FPGA, and if we do that in a careful way, it should, you know, be just like the previous KPN except for that process. And so we can make, let's say, application-specific KPNs. Okay. Eventually, to have genuine dynamism, well, you have to get through that FPGA, you know, compile. And early in the days of FPGAs, we had dreams of being, you know, very dynamic, and it turned out not to be practical. But that's, I mean, that's part of what's so appealing, is that, you know, maybe that's out there. I think it's certainly worth thinking about.
Okay, so with that, I think we conclude the session. So there is coffee and some refreshments out there that we can use for more discussion with Mike. And before we end, we have a tradition of giving this small gift.
Oh, thank you so much.
Okay.
Thank you.
Okay, thank you.
Thank you.
Thanks a lot. Okay, so